this was enough time for people to come in late. All right, sweet. Okay, so hello everyone. Welcome to week 4. There is an exam happening today, so that's why there's some people missing. So good luck to them. I hope they do well. But thank you for those who did come in today. Today we're going to be expanding a little bit more on kind of how we design things. The past couple weeks we've been teaching you the tools on, how to make things. But today we're going to be thinking more about the process on why you might design something a certain way to, optimize your parts for, your application. But before that, I'm going to introduce your final project. I talked a little bit about this last week, but basically, the final, again, don't worry too much about this because it's actually not that bad. But your final is just to kind of make anything you want. That's basically what it is. There's just a very loose set of constraints. Obviously, it just can't be something that we made in class previously, which is kind of self-explanatory. It must contain at least 5 design features. So, at least, an extrude will count as a design feature, or revolve, or like a fillet will count. So we want at least 5 of them. And I hope you know at this point, like 5 is actually not that many, right? We made more than 5 for the hair dryer, I believe. So you definitely have the ability to make more than 5 design features. The last thing is a little bit subjective. It must be designed with manufacturability in mind. This is a little bit like looser because it's kind of up to interpretation. But today I'm going to be talking about like designing for manufacturing. So obviously, if you didn't know, at the end of this class, you will have the option to have your finals 3D printed by me. So I'm going to teach you how to design stuff for 3D printing to hopefully give your final like its best shot at being, really solid and not like fall apart when I give it to you. So please make your finals with manufacturability in mind. I'm going to be showing some examples or be telling some examples of past finals that were not really designed for manufacturability. So I hope you can learn from their mistakes and make something really, really cool. But yeah, you've probably seen this slide already. These are some past finals. Obviously, in these cases, there's a lot more than just 5 design features. But again, even if you didn't have CAD experience, some of these finals were made by people who didn't know how to make anything coming into this class. So this is all feasible from this class. Obviously, if you're, really pressed for time, you don't have to make something this complex, but it's really awesome to see these up here. And it's really fun when I see them when I'm grading. So
are those actually printed out?
These are renderings. So we're gonna go over renders next week for your finals, but these are just kind of like digital renderings of the models. And then like when we print it out, it's all like one color and solid. So like when it prints out, it doesn't look quite as cool as this, but the renders are pretty awesome to see. So this is definitely something possible and attainable in this course. So if you spend some time on your final and make something awesome, I'll be happy. Also, sometimes people make like really, really insane finals that aren't really super 3D printable, and I usually just kind of like cut off like the design for manufacturability. So if you make something like super insane, but it's hard to 3D print, it's not that big of a deal. But I do encourage you to design things for 3D printing because it just makes my life easier, and then you'll have a nice final to show for it. Makes sense? All right, cool. So module 4, designing with manufacturing in mind. Keep in mind, I'm going to be rambling a lot today, so hopefully I don't bore you to death. I have brought some models that I'll pass around the class, like while I talk. Hopefully it's a little bit more interactive. But this is all important information for you to know, mostly centered around 3D printing today. But I'm going to go over some other manufacturing stuff too. All right, so when you think of manufacturing, a lot of the times, like especially in movies and stuff, you'll see people using subtractive methods, right? You know, some people are like hammering stuff, drilling things, or like grinding stuff away. That's all a subtractive process, right? You start with a block of material and then you cut away at it until you have the product that you're looking for, right? And this is a pretty common manufacturing process. Milling, drilling, and stuff like that is all considered subtractive, which is all on the next slide. So there's a bunch of subtractive processes you can see in the bottom right corner. There's me in high school with an angle grinder next to wood. Probably not the safest, but these are all subtractive processes, right? Typically, subtractive machines that are really precise, like mills and lathes, are typically very large and very expensive, especially when you get into the high precision stuff. They can cost like upwards of hundreds of thousands, sometimes millions of dollars for the machine itself, right? So unfortunately, a lot of these subtractive processes are a little bit out of reach for your everyday person like you and me, especially students, because we don't have that much money. So it's pretty awesome, but I'm mostly going to be focusing on additive manufacturing. But these do exist, and if you're curious about how to design for stuff like this, feel free to ask me later. But yeah. Additive manufacturing is kind of the opposite. I mean, kind of in the name. You start with nothing, and then you have some kind of tool that deposits material until you have your final product, right? So for stuff like 3D printing, it kind of does it in layers and layers until you have your final product. But there's other ways of doing additive as well. One of the other big ones is injection molding. If you're curious, injection molding is a form of additive manufacturing because you have kind of a mold and then you add material into it, right? So that's pretty cool. But we're mainly going to be talking about 3D printing today because that's what your finals are going to be made, or how your finals are going to be manufactured. But yeah, there's a bunch of applications for 3D printing. These applications are growing more and more as the technology evolves. Before it was just kind of limited to rapid prototyping and stuff like that, but it's starting to make its way into like full-scale production. So, some automotive companies are making parts that are 3D printed. That photo on the right is actually like part of a car called the C Zinger. It's like a hypercar company made in California. But they use like generative design and additive manufacturing to make their control arms and a bunch of other parts. So it looks super organic. And if you were to manufacture that in a traditional manner, it would cost a ludicrous amount of money, or it would be straight up impossible. So 3D printing allows for stuff like this, and it's pretty awesome. But yeah, there's obviously a bunch more bullet points there. Feel free to read it. But yeah, there's a bunch of applications. In terms of types of 3D printing, there's a bunch of them out there. I'm just going to list 3 today, but there's something called SLS, which is more on the industrial scale. It stands for selective laser sintering. Basically, they take the raw material in the form of a powder, and then they use a laser to precisely melt a really small area of the part. And then they'll cover that solidified layer with more powder. They'll shoot a laser at it again, and they'll do it, hundreds or thousands of times until you have your part, right? So it's pretty awesome. You can use some pretty strong materials like nylon and stuff like that. But as you can see in the photo, it's a little bit messy. It's a lot more industrial based, so it's a little bit out of scope for most consumers like us. However, there are like services that will do this for you, and it's pretty cool. A variant of SLS is SLM, which is selective laser metal, and it operates on a very similar principle, but instead of a powder like a nylon or something, they use some kind of powdered metal. So that's pretty awesome. It's making its way into more manufacturing settings. You can like pay people and pay services to just SLM stuff for you, which is pretty awesome. But again, it's a little out of scope for us because it can get kind of expensive. The more desktop version of this is something called SLA, where instead of a powder, they use a resin, almost like an epoxy. But this resin is activated with UV light. So they basically have a very high resolution, like almost like a display or a TV on the bottom that will precisely shine UV light. It'll partially cure the part, and then the build plate will move up a little bit. It'll shine another light, and it'll do that over and over again until you have a nice part. SLA is pretty awesome because you can get some pretty insane resolution, especially at really small scales. So a lot of people like to use it for 3D printing miniatures. People like to do like Dungeons and Dragons or like just little scale figures of like characters and stuff like that. SLA is pretty great for that. Unfortunately, I do not have an SLA machine, so I'm mostly going to be covering FDM 3D printing, which is in the next slide. But FDM or FFF 3D printing is typically what a lot of people think when they think 3D printing. It's probably the most common type out there, and it's probably the most accessible as well. Also, like FDM and FFF are basically the same. So if you see them like interchangeably, it's mostly because I think FDM is a trademark name. So like a lot of other companies will use FFF because FDM is trademarked by someone. I think it's Stratasys. So yeah, I might be using them interchangeably. But yeah, you might be wondering how this 3D printing process works. The way I like to describe it is it's basically a very fancy hot glue gun, but on a robot. So basically, there's a hot nozzle that heats up to some warm temperature, and then there's an extruder above with some, gears or something like that to push the material into the nozzle, right? And when you attach that assembly to a robot gantry, you can get something that is pretty precise um, to make pretty complex models, right? So it's kind of, self-explanatory at this point. At least I hope this makes sense to you. It's basically just a fancy hot glue gun. It extrudes material very precisely over and over again to make a 3D part. So now that you kind of understand the concept of 3D printing, there's a bunch of different settings that can be applied when you go to 3D print something. So the first one is the layer height. Basically, how the 3D printing softwares work is it takes your model and then it slices it into a bunch of 2D profiles, and then it'll stack the layers on top of each other until you have your part. So that's why it's called a slicer, if you're curious. It'll slice your model, right? And the layer height basically tells you how coarse or how fine to slice that model, right? So the more times it slices it, the more accurate your 3D printed model will be to whatever design you had before, but the longer it'll take, right? There's more layers for you to print, and each layer takes, a certain amount of time. So if you add more layers, it'll, typically come at a reduction in speed just because it takes longer, but you'll get more details, right? So when you're setting your 3D printer to print stuff like that, you're typically trying to find a nice balance between, quality and speed. The typical layer heights I tend to see, I typically print at 0.2 millimeters, but people print, 0.25 or maybe 0.15 or even less if they want more resolution. I, kind of found that 0.2 is a nice, balance between quality and speed. And you can see here on the left, there's a very coarse layer height of 0.8 millimeters, and then if you go on the right, it's a very fine layer height. You see the very coarse layers are very visible because they're taller. So if you want something quick and dirty, you can just crank up your layer height, and then it'll make your part, but it won't be pretty. But if you want it super nice, you can make your layers very small. One of the big disadvantages, or a disadvantage for changing your layer height, is the more layers you have, there's technically more points of failure. So if you're creating a more mechanical-based component, you might want to consider a coarser layer. 3D prints are the weakest in like the Z direction because the bonding between each layer isn't always as strong as the material itself. your part might break along that layer, and if you have more of them, you're creating more points of failure. So if you're creating something that's focused around strength, you might want to decrease or make the layer height a little bit taller instead of finer. But again, that can also depend on what you're making, the material you're printing, and how much strength you really need. I haven't really encountered that many issues with like printing at finer layer heights, but part of it is because I'm using pretty strong materials, so it's also part of that. Also, like I'll be talking about like print orientation in a little bit, but that also plays a big role in how strong your part will be. Other than that, there's more settings that you can apply. The main one being the number of perimeters. If you didn't know, 3D printed parts are typically partially hollow, right? A lot of the strength of your part actually just comes from the outside of it, and a lot of the inside material is not needed to get a strong part. So I'm going to be passing a couple samples around. You'll be seeing some of the difference between these parts. But you can manipulate the number of layers, and I'll talk about infill in the next slide, to make your part weaker or stronger. Obviously, if you increase the number of perimeters, you're increasing the amount of material you're using, and it's just going to be more time just because there's more material to deposit. So, when you're 3D printing stuff, you want to balance, speed and strength. So I have 3 sets of models here. They should all be grouped together. This is one group. I'll put it here. Feel free to pass these around. Basically, these are all the exact same model imported into the slicer, but I applied different parameters when I went to slice my part. So I just talked about the perimeters. You can see, more and less perimeters, left to right, or less and more perimeters. I typically recommend, if you want a stronger part, to increase the number of perimeters before you increase the infill, because the outer shell is what's providing a lot of the strength of your part. So, for high strength parts, I typically go at like 4 perimeters with 25% infill, and I would favor that over something like 2 perimeters and like 60% infill. The perimeters really give the part a lot more strength than the infill does. So if you're curious about that, I would recommend increasing infill if you want your, or increasing perimeters if you want strong parts. But yeah, other than that, the other thing that people change a lot is the infill density, and it's basically just how hollow your part is. You can probably see with the models that I'm passing around that one model has significantly more infill than the other, right? So I marked it. One of them has like 2 perimeters and 40% infill, and you can see like the density of like the cross hatching is a lot more dense. So that typically adds strength to your parts, but in comparison to perimeters, you're going to be getting a lot more bang for buck material-wise by adding more perimeters instead of infill. But sometimes you need a little bit of both. So yeah. I kind of stop these prints halfway through so you can kind of see inside. Typically, the top is going to be nice and flat, but you can see the holes on the inside. My laptop is done. But yeah, does anybody have questions on like the perimeters and infill and stuff like that? No, I'm kind of going over this quickly. Yeah. I hope this makes sense. All right. Okay, so the last thing here on the slide is supports. typically, you might have a design that doesn't need supports, like this cube here. It printed without supports at all. But sometimes you'll have a model where if you tried to print it without adding supports, it would just straight up be impossible. So if you look here at this model, there's this kind of cylinder shape extending outwards from this vertical one, and it kind of just sticks out in free space, right? Unfortunately, 3D printers are kind of subject to the laws of like gravity and stuff like that. So if you try to print this, as the nozzle is extruding it, the filament would droop because it kind of comes out like molten and soft. So it'll droop as it comes out, and then your print will kind of fail and it'll be really sad. So one of the things you can do to mitigate this is by adding sacrificial material that you will print underneath your model. It'll print over it, and then when you're finished, you break it off. Right? So that's what a support is. It's just a sacrificial material. It is something that is an option, but because you guys are designing your finals, you have the option as the designer to design the requirements for supports out, if that makes sense. So if you can design something in a way that avoids this, that's typically pretty optimal because one, you're saving just material because you don't need to print any supports. You're saving some time like post processing because you don't need to break anything off. You can just take the part off and use it. Um, and you're kind of saving on kind of surface quality. So if you print with supports, sometimes the interface between the support and your actual part isn't always going to be like perfectly smooth. So, try to design things to not require supports, but obviously if your design calls for it and you need it, it's a good thing, or it's a good option to have. In this case, like it's kind of hard to avoid using supports because, let's say, this design requires the cylinder to be out like that. But one way to mitigate the amount of supports is maybe having some kind of angled piece underneath that prints onto the model to help us support that overhang. But we'll talk about that in a little bit. But there's many ways you can design things to not require it. Yeah, this is another photo of supports. You can see here, like this beam isn't really need supports because there's nothing crazy overhanging, but the H and the T have these vertical or horizontal overhangs that require supports. There's a couple of ways you could go about fixing this. Does anybody have any ideas on how you can have printed these without supports? Yeah, exactly. So you could have printed, the H and the T just laying flat and then leave them out. But honestly, for the H, if the bridge isn't too long, you honestly may not need these supports at all. But for the T, the only way to fix it is by changing the orientation of your prints. So that's something to keep in mind. If you think about which direction your 3D printer is going to print your part, you can avoid certain situations like this. Right? This person wasn't really thinking they printed them straight up. But again, depending on your needs for your part, you might purposely print in this orientation. Right? So again, like I said, prints are strongest or weakest in the Z direction. So if you print something that needs to be strong in a certain direction, and you print it in the Z direction, then you can make your part really weak. So sometimes I'll purposely print something in an orientation that seems like counterintuitive to get the maximum strength out of my print. Anyways, with all of that in mind, I'm gonna, or we're gonna run through a quick demo of how to slice your parts for 3D printing. So we're gonna use a program called Prusa Slicer. It's an open source slicing software that a bunch of other slicers are based off of. So again, like I was saying before, you will use a slicer to convert your 3D model into a set of instructions for your 3D printer to listen to. You'll basically, take your model, cut it into a bunch of slices, like I said before, and then it'll create a toolpath for your prints to follow. So again, we're using Prusa Slicer today, but there's a bunch of other options out there. So this is the more interactive part of today. You just want to download Prusa Slicer, which is right here. Oh, wrong link. Great. It should be this one. Yeah. You want to download Prusa Slicer. It should be pretty fast compared to Fusion. It's a lot lighter of a program. Okay. I might have to update my program. Yeah. Is all of this making sense to you? Because I know I'm rambling a lot, but I'm hoping this information is kind of getting into your head because it's some good to know stuff, but I understand if it's a lot. Okay, I'm going to update this real quick. Also, because people are here today, you have the opportunity to get free stuff. So I've been printing a bunch of stuff, as you can see, and feel free to take some and bring them home because I don't know what to do with them. So yeah, one of the things that we're going to be slicing today, or I guess the only thing, is a 3D benchy. And as you can see, I have a giant bucket of them because I use them for calibrating my 3D printer. So yeah, please take them because I print like a bajillion of them and I don't know what to do with them. But I digress. You can come and get it in a little bit. Who is still installing Prusa Slicer? Okay, no rush. I think it's just because I already had it installed. All right. So once you have that installed, it'll probably greet you with, a screen like this. If you don't see that, then just go into printer and then add or remove printers and then add or remove presets. Your screen should look a little bit different because I have a bunch of printers, but yeah. So basically what we're going to do is we're going to all select the same printer because, different printers have different capabilities. And then in turn, they'll be printing faster or slower. So if we can all have the same printer, then the G-code output should be the same and the time should be the same. So that kind of helps me when grading. So it should greet you with this screen. You can kind of click through it. You can log in if you want, if you have a Prusa account, but I don't, or I do, but I'm not going to log in. I'm going to skip this or hit next. Oh, great. Okay. But then you should be greeted with this. So these are a bunch of printers available that you can use. We're all going to select the same one. So for consistency's sake, let's all just pick the Prusa Core 1 with the high flow 0.4 millimeter nozzle. So it should be this check mark right here. Again, if you're not using the same printer, then it's not going to give you the same G-code output. Please use the Prusa Core 1 with the high flow 0.4 millimeter nozzle. I usually have to say this like 3 or 4 times because someone's not going to see this and then they're going to click on the wrong one. But yeah, please use this one. With that, you can just press finish. The rest of the stuff is just like if you have an SLA machine or if you have a machine that's not a Prusa machine. There's a bunch of, basic configurations, but, for our sake, we're just using one printer. So I'm just going to press finish. Over here on the right is your selection of printers. It should be a lot smaller than mine unless you have other printers. But I have a couple printers and I have a bunch of different presets for it. So yours should be this one, the Core 1 high flow 0.4 millimeter nozzle. Oh, I'm going to switch this back. So similar to Fusion, you kind of have this big workspace here. This is what we call the build plate. Basically, it's the platform at which your print starts to be made from. But now that we're in this environment, we need to add a part to it, right? So what we're going to do is we're going to add the 3D Benchy. So just go here. There's this link where you can download the model. Down here, if you go to files, just skip this print file and then find the STL files. So you want to go under model files and then download the STL. So similar to last week where I was showing you like GrabCAD library and stuff like that, printables is another great place to find models. But this is typically more for 3D printing applications. So most of the models here are geared towards printer stuff, but it's a great place to find stuff if you're looking for it. But yeah, I'm gonna actually just download this again. Okay, cool. So once you have that downloaded, you can insert it. I'm just gonna do Control I, but I'm pretty sure you can do File Import over here if you don't want to use the shortcut. You find the file and then you open it. So here we have our model. Oh yeah, for the controls are a little bit different compared to Fusion. Holding left click is the orbit function, and then holding right click will pan side to side, and then you can zoom in and out just like normal. But yeah, you can see here we have this model of the Benchy. If you didn't know, the Benchy is a very like classic 3D print, and it's mainly because people use it as a calibration print. There's a lot of different um, design features on the 3D Benchy that typically 3D printers have like quote unquote like a hard time reproducing. So this is kind of a torture test of sorts to make sure your printer can, make high quality prints. The rule of thumb is typically if you can print a really nice Benchy, then basically anything that you try to 3D print will turn out pretty nice. Uh, assuming the fact that the part was designed correctly. Um, but you can see here, like right here, there's a big overhang. So if you don't have good cooling on your printer, this hull can droop. Same with like right here on the top, there's a bridge that if you don't have good cooling, it may not look good. Um, there's other features like this smoke stack. This is all I'm talking about cooling a lot because my printer's been running into cooling limitations. Um, but there's a lot of small features like on the bottom, there's some text. So if you have a bad first layer, it may not look very good. There's a really small sign in the back, and then like other features like that. So typically, if you can print a good one of these, you're pretty golden. We're gonna slice one, um, and I'm gonna enable a bunch of settings in a way that you probably wouldn't print a Benchy in. But for this assignment, I'm just enabling all of these functions just to show you how they work. Specifically when it comes to like supports and stuff, you're not really going to be printing a Benchy with supports. But for today's assignment, that's what we're going to do just so we can show you that function. Okay, I need to update this slide because the core one is the new one, not number 4. But basically, we're going to apply a bunch of these settings. Oh, this should be core 1. Okay, yeah. For this assignment, obviously we're using Prusa Slicer. We're using the core 1, but we're going to change some of these settings. So we want the perimeters to be 3. We want the resolution or the layer height to be 0.15 millimeter on the speed profile. And then we're going to change the infill, and then we're going to enable supports. So I'm going to kind of do these out of order. I typically, specify the resolution or the layer height first. So if I go into the Prusa Slicer, you can see here under print settings, you can click it and you can see there's a bunch of different layer height options. There's a couple of different 0.15 millimeter layer height options, and that's just mainly based on how fast it's going to print. So in our case, we're going to just use the speed profile, so just 0.15 speed. And then I'm going to start setting some of these parameters. Also, side note, for the filament type, just make sure to use generic PLA, because if you use a different material, you're going to get a different time, because some materials require more cooling than others, and it might slow or speed up the print. So if we all keep it at generic PLA, it should be the same for everyone. Yeah, I'm going to change the perimeters and the infill. There's a number of ways that I could go about doing that. You can see the infill setting is over here. So I could change that from 15 to, what was it, 20? I can change it over here. Or I can go under the print settings tab up here on the top left, and it'll give you a more like bigger breakdown of all the settings that you can change. So over here, I can go down to infill and I can modify this. Obviously, I already changed it, but you can change the infill here. You can also change like the infill pattern and stuff like that, but just leave it as is, or else it's going to affect your print time. But these are all options you can change. For the number of perimeters, I can change that under layers and perimeters. So I can go here. My perimeter count is right there. I'm going to increase it from 2 to 3. Looks good to me. And then there's turning supports on. So typically for Benchy, like I said, you're not going to enable supports, but I'm just showing you how this function works. So if you were to slice something that required it, then you can use it. So there's a generate support material checkbox under support material. I'm going to enable it. And then I'm going to leave support on build plate only off, just to add supports everywhere. So it will auto generate supports with this check mark. And we can see what it looks like by slicing it. So if I go back to the platter on the top left, I can hit slice now. The computer will think, and then it'll generate a toolpath. My computer is slow. All right, cool. So here you can see this is what the model is going to look like after you print it. All this green stuff is the support material, right? So this is all sacrificial. You can see all the statistics here, which is really nice. So you can see like, you know, the support material is going to take, you know, 3.74 grams plus like 0.2. So like 3.94 grams. That's not like that much weight, but you know, if you're printing, you know, hundreds or thousands of boats, you might want to not have supports because that's just a lot of material that you're wasting. But there's a lot of cool information here. If you want to look at the specific toolpath, there's two sliders. Over here is the vertical slider and then the horizontal slider. The vertical slider will show you each layer, kind of giving you a breakdown. And I find that this is probably one of the best ways to visualize how a 3D printer works, besides just watching it. But you can see here, this is the first layer. I'm going to drag this to the beginning. But you can see over here is the G code. So this is basically a really long set of instructions that your printer follows. It's kind of sad, but I can kind of read this because I've been looking at this stuff for so long. But like a G1 command is like a movement command. And you can see there's like thousands and thousands of lines of command instructions for the printer to follow. And you can see the arrow is kind of a representation of the nozzle. So you can see it'll go around. In this case, it starts by printing the base of the support material, and then it'll start filling in the whole first layer. So it starts with perimeters, and then it'll fill it in, and then that's the first layer, right? And then you'll see, I'm going to just go up in layer. You'll see the printer will do that again and again. There's the infill. You see it's nice and hollow, and it'll just do that many, many times until you get your part. So over here, you can see here that there's a total of 500 layers that this printer has to go through to make your model. And it'll do that for like every single part you make. So you can see this is kind of how the slicer works. You can technically say like a 3D printer is like a 2.5D printer. If you played like 2.5D games where it looks kind of 3D, but it'll basically just stack a bunch of 2D profiles on top of each other until you get a 3D part. So 3D printers are technically not 100% accurate, but they can get pretty darn close. So yeah. If you followed all of the settings properly, you should get a time that's very similar to what I have here. So under normal mode, it should be about 1 hour and 6 minutes. If you're using a Mac, sometimes the time estimate will be like 1 hour and 5 minutes, but they should be within like 1 minute of this time here. So yeah. if you did it right, this should be good, and you can just take a screenshot for this assignment. But yeah. One thing to note is if you ever make a change to any of the parameters that you make, so in this case, let's say I want to change the number of parameters. Every time you make a change, you're going to have to reslice your model, right? Because it has to recompute the toolpath for your printer to follow. So every time you make a change, you're going to have to slice it again before sending it to the printer. But yeah. Does anyone have any questions about this? I hope it's pretty self-explanatory. Okay, sweet. But yeah, you should get about an hour and 6 minutes or an hour and 5 minutes. So if you don't have that, feel free to raise your hand now and I can look at it, or you can try to figure it out on your own. But yeah, this time is wrong now because I just changed the number of perimeters. Cool. All right, sweet. All right, so now that you kind of understand how a 3D printer works and you kind of understand all the settings, this is kind of the meat of today, where we're going to be talking about 3D printer limitations and designing for manufacturing. So one of the big things that people talk about when it comes to 3D printing are overhangs. Similar to the support that I was kind of talking about earlier, there's kind of a threshold for 3D printed parts where if you cross it, you might need supports, but if you are at the limit, then you may not need supports. The general rule of thumb is don't really have anything over 45 degrees overhanging outwards from the part. So you can see here on the left, it's a very shallow overhang, maybe that's like 20 degrees, 30 degrees. It's not shooting out that much. So your 3D printer typically won't have a problem having an overhang like that. But as you start to go farther and farther out with a more extreme angle, it requires a little bit more cooling to the point where the printer might just fail. If you want to take a really close look on like a layer by layer basis, one of the reasons why the overhangs can become so difficult is the layers will, obviously stack on top of each other. But if the overhang is so great, there's no material for the layer or for the nozzle to print on top of. So you can see up here where the overhang is very shallow, there's a very large amount of overlap between each layer, right? So for reference, like most 3D printers come standard with a 0.4 millimeter nozzle. So, there's a very small offset here and the printer's not really printing in midair. Maybe like, 10 or 20% of the extruded material is kind of printing in free space, but the rest of the material can kind of hold it up and it's pretty, like it can still print pretty well. But when, for example, you get to a slope like this, you can see if you look really closely, as I get farther and farther to the top, the amount of material here attached to the previous layer is getting less and less, right? So here it's almost the whole thing, and then as we get to the top, it's basically nothing. And you can see here, like even the slicer will recognize this because this overhang, has these blue sections where it's completely unsupported, right? And typically, if you have a really steep overhang for a really long time, the printer will have a hard time reproducing it, and then it'll either droop a lot and it'll look really ugly, or the print will just fail entirely. So that's why we typically use the 45-degree rule. The other reason is like 45 degrees is just kind of a nice number because it's in between 0 and 90. So when you add like a chamfer and stuff like that, those are all, pretty standard at 45 degrees. So when you chamfer stuff, you add that overhang, but it's a nice even number and the printers can reproduce that pretty well. in some cases you can go like farther, and like a lot of modern 3D printers have better cooling capabilities, so you can kind of push it a little bit farther than 45. But the general rule is just, you know, don't go more than that unless you really, really have to. Does that make sense? Okay, cool. So overhangs are almost everywhere in your part, and there's some places where you may not have noticed them before. One of them being holes, right? If you think about holes and stuff like that, and you draw like a tangent line as you go farther and farther closer to the top of the hole is an overhang, right? So it's very similar. I mean, this is basically, you know, a semicircle, so it's half a hole. But this side of the hole is where the overhang lies, right? You can see here, you know, in the blue, right? So sometimes when you're printing a really small hole, your printer just has enough cooling and it's like small enough that it doesn't matter that much. But when you start printing larger and larger holes, sometimes it can start to droop, right? Part of it is if you have a good printer with good cooling, but part of it is the model, right? So one way people avoid this drooping is by changing it from a normal round hole to a more teardrop shape. So if you see here, this teardrop shape adds kind of a triangle on top of your hole, and that ensures that the overhang angle always is below or at 45 degrees, right? So sometimes you might be worried that like, oh, like it's not a perfect hole anymore, but for a lot of cases, this actually works perfectly fine. So if you see a lot of vertical holes like this, and you see people model them with like this teardrop shape, then you know like they were really thinking about, you know, how this might be printed, and you know, this can reduce supports. So if you're making vertical holes, unless your part really, really needs to be a circle, you can get away with stuff like this. Obviously on the Benchy, it doesn't have that teardrop shape because it's supposed to be a torture test. But you know, if you were to modify this to be easily 3D printable, you could change this and make it more teardrop shaped. The other thing is bridging. Basically, in some cases, you'll have a part of your model where there's a span of two places with nothing in between, and that's what we call a bridge. So it's kind of similar to that unsupported model that I showed you with the cylinder sticking out, but you know, in this case, there is something on the other side. And 3D printers are capable of bridging over shorter distances. So you can see, like on the Benchy here, if I can find it, like the front of like this window on the top, there's this bridge, right? It's marked in blue again, but you can see there's nothing supporting this from either side, but the printer is capable of reproducing this over short distances, right? So if you have a short bridge, you can see sometimes the printer's cooling can keep up if it's dialed in well. But as you get to have longer and longer bridges, it starts to droop more, right? So I had a student and we were telling them, you know, don't make long bridges. They submitted like the Golden Gate Bridge. So like, please don't do that because one, like the model looked great, right? But in terms of printability, is very, very difficult to print. And uh, at the time, our printers weren't as good. So we tried to print it, but it failed almost every time. And the model was so small and intricate that when we handed the final to the student, it like disintegrated in their hand. And it made me like kind of sad because they're like, they spent so much time modeling it and then it just like fell apart. So please like avoid long bridges because, you know, it might require support material, um, or it just might not look great. So again, because you're the designer, you can design out the requirements for long spans unless your model really requires it, right? So it's kind of like uh, a balance of, you know, what your part really needs and what you can model out. So try to avoid really long distances unless you know that you need it and you might have supports there. Yeah. Does that make sense? Yeah. Cool. One of the other points here is thermal expansion and tolerancing. Because 3D printing, relative to other processes, is relatively imprecise. Imprecise is in quotation marks because you can dial in a printer to be pretty good. A lot of high quality like milling and subtractive manufacturing machines like measure things within thousands of inches. A 3D printer isn't quite that precise, but it can get pretty close. Typical tolerances of a 3D printer are usually like 0.2 to 0.4 millimeters. So your part might be a little bit bigger or smaller than about that amount. If you have your own calipers at home, you can see that that's a pretty small amount, but it's also not insignificant. So you might want to factor in some of these when creating parts, especially when you have parts that interact with each other. Because in Fusion, there's no thermal expansion or anything like that. It's just the model. So you can model something that looks great, that interfaces perfectly, but if you don't account for some real world tolerances, you might have some fitment issues. I'll show you on the next slide. But yeah, you want to kind of account for that if you have other parts meshing with each other. Um, for example, one of the things I do is I use a lot of M3 hardware in my 3D printing parts. So if I want a hole that the bolt can slide through nice and easily, I'll typically increase the hole diameter in the model to be 0.2 millimeters over the nominal diameter. So, an M3 bolt is 3 millimeters in diameter, but I'll add zero point 0.2 and make it 3.2 millimeters so I can have a nice smooth hole. I don't have to like thread it through, if that makes sense. So sometimes adding a little bit of tolerance into your designs can be really useful. Sometimes it's just an experience that you'll gain if you do it more often, but hopefully this makes sense to you now. The other thing that you might want to keep in mind is elephant's foot, because sometimes 3D printers aren't always perfect when it comes to their first layers. Um, and when it comes to bed adhesion, a lot of people like to squish the first couple layers down a little bit to make sure the part doesn't fall off. And when that happens, there's a little bit of extra material that gets extruded, and then that gets pushed out to the outside of the model. So if you see here, in the circle here, this model, in this case, looks like kind of squarish, but the first couple layers are kind of squished outwards, and it extends beyond that initial phase. So sometimes that's not good because you might want this to be exactly this amount. And if you're trying to make these fit together, there's extra material that is in the way, right? So one of the things I like to do is I basically just chamfer almost every bottom surface that's connected to the 3D printer. Because if you add a chamfer, it'll kind of cut in at 45 degree here. So again, it's a 45-degree overhang, so it's not an issue for the printer. And then any elephant split that happens will get squished out into that extra space that you just gave. So if you have a little bit of a chamfer, that extra squished out from the elephant split can typically be a non-issue. If that makes sense. So these are just little small like tips that I picked up over the years when printing stuff. But hopefully it's useful to you. But yeah, with like better tuned machines and stuff like that, elephant split is becoming a little bit less of an issue, but it's not always never an issue. So it's a good idea to factor in a little bit of tolerance just in case the printer that you print on isn't like fully dialed in and stuff like that. The other thing, I guess I'm kind of going backwards at this point, but warping is sometimes an issue on 3D printers. It's become less of an issue now, again, because 3D printers have gotten better. But depending on the material that you're using, sometimes the corners can lift and warp in the top right corner. But there are ways to mitigate this through your designs. So one of the reasons why large pieces will warp is that there's a lot of stress at all the corners when the prints cool down. So if you think about thermal expansion, this is kind of technical, but if you think about how a print will cool, material will try to pull itself into each other just because of how it cools and how parts will contract when they get colder. So when that happens, it can be strong enough that it lifts from the corners of your parts. But the way to mitigate that is to reduce the number of sharp corners because the sharp corners will kind of create a stress concentration. So in this case, they printed a cube and the corner is where all the stress was and it pulled so hard that when it cooled, it lifted. So again, this is less of an issue if you have a really well-tuned machine, but to give your prints like the best chance of success, sometimes rounding the corners just even a little bit can help make those stress concentrations a little bit lower and increase the chance of success. But yeah, this is not a super big deal these days, but it can be an issue. Also, when you print really large parts, because the parts are so large, there's more forces on the corners. So larger parts typically have a tendency to work more than smaller parts. So yeah, keep that in mind. Okay, yeah. So this is a good example of poor tolerancing. So this is actually a final from, I believe, 2 years ago. Someone designed this kind of Lego shaped person, but they didn't account for tolerancing properly, right? So maybe the head fit on right, but when we tried to put the torso onto the legs, you can see we couldn't get it farther than this without risking breaking the model, right? And it's probably because when they modeled it, um, they had zero tolerance. So let's say like the inside hole was like, I don't know, 2 millimeters, and then this pin was exactly 2. When we went to put them together, because there wasn't enough tolerance, the prints didn't fit together. So to avoid this, if you have like a multi-part assembly, you might want to oversize one of the holes or undersize one of the pins. So this is just an example of that. But I hope that makes sense. Yeah. All right, cool. But yeah, that's basically all I have for today. I hope you're paying attention because there is a quiz on all the stuff I've talked about. I'm pretty sure I covered everything, but yeah, there is a quiz. I hope you knew that it was coming because you have the slides, but it's open note and I'm gonna be here. Also, you have infinite attempts, so oh no, like it's gonna be super hard. But yeah, basically it's just a quiz to test your understanding of what I said today. And if you maybe missed something, this will hopefully correct that. Just to give you a little bit more knowledge for your designing for 3D printing stuff. But yeah, feel free to take that now. Other than that, that's basically all I have for you. So today was nice and short. I think you gotta leave soon. But also, if you want a benchy, please take some because I literally have a crap ton up here. So come take some. I also have some cool like 3D printed dinosaurs that are like multi-color and stuff. Um, these are kind of interesting because these are only manufacturable by using a 3D printing process because all these links interlink with each other as they print, and it's all print in place. So it just printed like this flat. Yeah, come get your models or come get your benches or whatever.